Let's talk about the action potential. This is some really cool physiology here. In order to talk about the action potential, we have to start by talking about our old buddy, the sodium-potassium pump. So the sodium-potassium pump is found in membranes all through your body. These little things look like little people that have no arms and bodies. These are phospholipids, all right? So remember, the phospholipid bilayer, the plasma membrane, goes around all the cells of your body. Therefore, we have the extracellular fluid, the water outside of the cell, and the intracellular fluid, the water inside of the cell. What the sodium-potassium pump does is embedded in that phospholipid bilayer. It's constantly pumping 3 sodiums out into the extracellular fluid and 2 potassiums into the intracellular fluid, all right? And it costs 1 ATP. You have to spend 1 ATP to ride this ride, okay? So why is that a big deal? Because as a result of that, remember, this burns something like 40% of all your ATP at rest. So like on a 2,000 calorie diet, this is 800 of your damn calories right here. Just powering the sodium-potassium pump. What's the big deal? Well, it means throughout the ECF and ICF of your body, there tends to be more sodium out here and more potassium in here. Now sure, there's still occasional potassiums out here along with lots of other stuff, calciums and phosphates and all kinds of other things. And there's still some sodiums and other things in here. But right next to the membrane anyway, as we get further into the fluid, things tend to even out. But right next to the membrane, there's lots more sodiums on the outside of the membrane and lots more potassiums on the inside of the membrane, all right? And as a result, notice there are 3 positives go out and only 2 positives go in. Therefore, there are relatively more positives out here and fewer positives in here. So fewer positives in here, remember electricity, less positives, the same as more negative. So as a result of the sodium-potassium pump, there is a default charge on the membranes, all right? What is that charge? Negative 70 millivolts, all right? Because there are more positives here, fewer positives here, the inside of the membrane is relatively more negative. We call that the resting membrane potential, the RMP. Notice that's not the RCMP, that would be the Royal Canadian Mounted Police. They're not here. But I bet most of them still have a resting membrane potential around negative 70 millivolts. So we now have the setup. It's as a result of the sodium-potassium pump that we've created this difference. It's both a concentration gradient and an electrical gradient. More sodiums are concentrated out here, more potassiums are concentrated in here. And it's an electrical gradient because the inside of the membrane is now more negative relative to the outside of the membrane. So, having done that, let's get rid of the sodium. I drew the line here to indicate that this is everywhere. This is kind of a separate topic. Now let's focus on the action potential. Now we're going to look specifically at the axon hillock. So I'm going to erase this, but don't forget that this is here. It's what allowed all of this to happen, okay? So in the axon hillock, remember, let's just kind of review. You had, on the dendrites of the neuron, you had graded potentials, all right? The dendrites, there are synapses on the dendrites, releasing neurotransmitter onto ligand-gated channels. That was opening either sodium or potassium or chloride channels, creating either EPSPs or IPSPs, positive or negative currents. And those were all converging in the axon hillock, okay? So let's do a little graph of what's happening. So here we are at resting membrane potential. Here we are at negative 70, all right? As the graded potentials start to sum up in the axon hillock, it causes us to become more positive. We're assuming in this case we have more EPSPs. So a positive current causes us to get more positive until finally we hit that special magical value that's going to trigger everything. And what was that special? That's not a straight line, is it? Good Lord. You'd think after all these years I could make a straight line. This special magical value, what was it? It was roughly negative 55 millivolts. And what did we call that? We called that threshold. And what happens once we hit threshold? It's going to start opening the voltage-gated sodium and potassium channels. Now here's the thing. Voltage-gated sodium channels open instantly, whereas voltage-gated potassium channels take a little longer to open. So the sodium channels open and shut really rapidly. Boom. Potassium channel is slow to open, slow to close. So it's like all at once? Yeah, you try that. Yeah, whatever. So, as a result, the first thing that happens here, both channels have been signaled to open, but it's happening faster for the sodium channels. So here in the sodium channel, what I'm showing here, the see sodium blue, channel blue, picking up on, are you picking up what I'm putting down? So green channel is the potassium channel. These are gated channels. They're not always open. They have a gate that's normally shut, okay? Now the potassium channel just has one gate. It's normally shut. The sodium channel has two gates. It has what's called the activation gate and the inactivation gate. The inactivation gate is normally open. When we hit threshold, it opens the activation gate. So once we hit threshold right here, the activation gate opens. All right, so now it's open as well. Now both gates are open in the sodium channel, all right? What happens now that both gates are open? Sodium comes through. It's like when you got a sink full of water and you pull out the stopper and drains the sink immediately, doesn't it? So what's going to happen? These sodiums are going to come rushing inside of the membrane. There is now going to be a cajillion sodiums in here. Many, many, many more sodiums than normal. Sodiums all over the damn place, all right? Tons of sodiums. And what does it happen then? What happens to the resting membrane potential when all these positive charges come in? Well, it's going to change this. It's not going to be -7 anymore. It's going to go up to like +30, +35, +40. Doesn't matter exactly. We don't care. Let's say +30. So what's going to happen here is we have the rising phase of the action potential in which we go all the way up to, let's say, +30 millivolts, all right? The inside of the membrane becomes depolarized. Depolarized means going closer towards zero, all right? And in fact, above zero in this case. All right, what happens now? Well, after a few moments, it's the sodium inactivation gate that shuts, all right? Sodium inactivation gate shuts. What happens when the sodium inactivation gate shuts? No more sodiums go through. And right around the same time that the inactivation gate closes, the potassium channel now finally opens, all right? Now the potassium channel opens. So what happens when the potassium channel opens? Same thing we saw before. It's like you got a sink full of potassium, you pull out the stopper, and so what's going to happen here? Well, we're going to start heading in the other direction. The sodium made it more positive. Now when the potassium leaves the inside of the cell membrane, there are going to be less positives in here, which means more negative. So as a result, we start coming down. This is the descending phase of the action potential. All right? So now all these potassiums, they're all going to go flowing out. All the potassiums that were being held in here against their will, because the gates were closed, they're now going to be able to head out to pasture. All the potassiums flowing out here. Tons of potassiums. Potassiums everywhere. So many damn potassiums, you got to be careful not to step on them. They're all over the place. Okay, so, and in fact, what's going to happen is, not only do we go back to the resting membrane potential, we let so many potassiums out, we go a little too negative, all right? That'll become important in a moment. Or maybe not, we'll see. So around this time, all right, the sodium activation gate is shutting again, but there's a brief period of time during which the sodium channel is completely closed, all right? And during that period of time, even if we had another stimulus coming in, graded potentials coming in on the dendrites, this sodium channel is locked shut. This is locked shut until that inactivation gate pops open again. So what does that mean? There's a brief period of time during which we cannot have another action potential. And what do we call that period of time? The absolute refractory period. No action potential possible. Right? So, this potassium gates are going to close again. The action potential only lasts a very brief moment in time. All right? And then eventually the sodium channel resets. All right? We cock the hammer back on the gun again. So now we can have another action potential. The sodium inactivation gate goes back to its normal state, all right? Now things have apparently returned to normal, but we went below resting membrane potential. We went all the way down here to maybe like negative 90. So now what happens if we get more EPSPs? Well, originally we only had to go from negative 70 to negative 55 to get the threshold. Now we got to go from negative 90 all the way to negative 55. So we need a supra-threshold stimulus. In other words, it's going to take a stronger than normal stimulus to get us to threshold the next time. So during this period of time, you can have another action potential, but it takes a stronger impulse. What do we call that period of time? The relative refractory period. And so eventually then, things will start going back to normal. But wait a minute, how do things get back to normal? Look at what has happened here. Oh my God, as a result of the action potential, all the sodiums which are supposed to be out here are in here, and all the potassiums which are supposed to be in here are out here. Everything is back-asswards, upside down, inside out. How in the world is the world ever going to return to normal again? It's what we had right here and we erased. The sodium-potassium pump. It's working 24/7, 365. Just like Nico's, those guys are working 24/7, 365. So what happens? Within a short amount of time, the sodium-potassium pump restores the world to normal, pumps all those sodiums back out again. All right, all the sodium's now going to be back out here. All right, and it's going to pump all the potassiums back inside. So now everything is the way it should be. Right now the birds are singing again. The flowers are growing in the fields. Everything is wonderful. So that was the action potential, all right? So I should have kept this up to date. When we got down here, we went down to negative 90, went too far, and then what happens as a result of the sodium-potassium pump, we are eventually returned to normal, to negative 70, and now everything is right again. We can have normal action potential, all right? So look over that again. See, it's not that big of a deal. The action potential is really cool, actually. It's amazing the way it works. And remember what made it all possible? The sodium-potassium